All right, guys, today we're going to do the last section of Chapter 8, which is 8.6, Solving Rational Equations. I can solve rational equations and identify any extraneous solutions. That's a fun word to say. But again, this is we're going to explain what all that means. But I want to go back and start with a problem maybe that we've probably seen in Algebra 1. We probably avoided it, to be honest with you, because we didn't really want to have to deal with it. So let me just give you this one example here of an equation that we didn't really realize was a rational equation, but it really was. So I'm going to start with negative 1/5 plus x over 3 equals 2 over 15, or 2/15. Okay, so we would have had this type of problem, and one of the things that really bothers us about this type of problem, obviously, is because it has fractions. We hate fractions. And so that's actually one of the issues is we need to clear these fractions out, because the goal is always the same, right? When you're solving equations, you want to try to isolate the variable, and there's your variable right there. Well, the issue is right now that x is being divided by 3. But that's not the only issue. You've also got a 5 over here. You've got a 15 over here. There's all kinds of fractions in this problem, okay? What I want you to think about is if, for example, one way that I could try to tackle this is if I could multiply by a common denominator, then it would clear all of my fractions out. Because remember, a fraction is nothing more than a division problem. For example, I've got negative 1 divided by 5, I've got x being divided by 3, and I've got 2 divided by 15. If I could undo those through inverse operations, then it's going to clear all of these fractions. Well, let's just think about our denominators and what we have here. We've got a denominator of a 5, and a 3, and a 15. Well, what's a common denominator between 5, 3, and 15? Well, obviously, the common denominator between 5, 3, and 15 is actually 15. So watch what I'm going to do here. I'm going to multiply this first term by 15. I'm going to also multiply this second term by 15. And as a matter of fact, I'm going to multiply the third term by 15. Now, the reason that I can do that is as long as I do it to every single term that's in this problem, it's perfectly fine. I've not really changed my problem. I've just amplified it or made it bigger by 15, okay? So what I want you to notice is what happens, though. Now I've got really 15 over 1 times negative 1 over 5. Well, what happens here diagonally? What happens with the 15 and the 5? Well, 5 will go into 15 3 times, right? And so this then would become a 3, and 5 would go into itself, of course, 1 time. So that's really going to go away. That's going to clear that fraction out, okay? Notice what happens over here. 3 will go into 15 5 times, so that one's going to turn into a 5, and this one's going to get cleared out. And then what happens when I take 15 divided by 15? Obviously, those are both going to go away. What I want you to notice is what just happened to our problem. All of the denominators just got eliminated, okay? And now I'm left with negative 3, because I have 3 times negative 1 right here, plus 5 times x equals, very simply, 2. So amazingly, this huge gargantuan type problem that I had that was very intimidating has become a very simple 2-step equation. So obviously I'm going to add 3 to both sides, and 5x will equal 5. And of course, if we divide by 5, we're going to get x equals 1, okay? So very quickly I was able to get to an answer of this problem that looked like it was going to be a very difficult problem. Well, we actually use the same type methodology to solve rational equations. So I want to actually look, we're going to look at 4 examples. I'm going to try to do this as quickly as possible. And we may cut that down to 3. We'll see here. We've got 1 minus 5 over 3k equals 1 over 3k, okay? So again, the issue is here, I need to isolate the variables. I need to get this k by itself. Right now, I'm dividing by 3. I'm also multiplying the 3 times the k. There's all kinds of issues that are going on here, right? So I need to be able to clear these fractions. Well, the issue is I've got a whole number over here. But remember, I can write any whole number as a fraction by simply just putting it over 1. So now I have 1 over 1 minus 5 over 3k minus 1 over 3k. What's a common denominator between 1 and 3k and 3k? Obviously, 3k. So I'm going to multiply everything here by 3k, just like I did in my example problem. And look what's going to happen. Obviously, here nothing's going to really cancel out. So that just gives me 3k times 1, which is 3k. Notice here, though, what happens. My 3k's completely go away. So I've got minus 5 equals, again, my 3k's go away. So it equals 1. Again, this huge problem that I started with now has been minimized to just this, okay? So add 5 to both sides, and I end up with 3k equals 6. When I divide by 3 on both sides, I'm going to get k equals 2, okay? So very quickly, again, you can see how that this works out, and we're able to use the common denominator to help us figure out what's happening here. Let's go ahead and skip to a little bit more of a complex one. Actually, I don't want to do that. I want to keep going on. So this will be example 5. And the reason I'm numbering them this way is because this is the numbers on your paper. You're going to be doing the even problems. But I wanted to give you some examples of what you're going to be looking at. So 1 over p plus 4 over 6p equals 2 over p. Again, we're looking at our denominators, and we're looking at the fact that we've got fractions everywhere. I know that if I could multiply by a common denominator, then I could clear these fractions out. So I have p and 6p. So my common denominator between these three things would in fact be 6p. So here's what I'm going to do. I'm going to multiply everything up here by 6p. Okay. Now let's just take a look at what happens here. So multiplying everything by 6p. Notice what's going to happen here. My p here and my p here are going to go away, but I'm going to be left with this 6. So 6 times 1 is going to give me 6. Okay, up here on this section, 6p and 6p are going to go away. So the only thing I'm going to be left with is p plus 4. And then over here, again, the p's are going to go away, but the 6 is going to remain. So 6 times 12, or 2, equals 12. So I've got some like terms here, 6 and positive 4. So I've really got p plus 10 equals 12. Which means now p equals 2. And you could actually put this back into your original problem just to see that it works. So I would have 1 over 2 plus 2 plus 4 over 6 times 2 equals 2 over 2. So let's just do some simplifying here. 2 plus 4 is 6. 6 times 12 is 12. So I've got 6/12, which actually simplifies to 1/2. So 1/2 plus 1/2 equals 2/2 or 1/2. So you can see how that solution did in fact work and was successful. So let's go to a little bit more difficult of a problem here. And actually, I want to go ahead and skip to this last one, because this one will kind of do all of it. And this is not one that's on your paper. It's just one that I pulled out from some archives here. But it is very similar to some of the ones you're going to have. Sorry, that x minus 1 should not have been there. Let's go back and do that again. 2 over x plus 6 over x minus 1 equals 6 over x squared minus x. Okay. All right, so let's take a look at this. And again, this is a little bit more difficult of a problem. This is very similar to some of the ones that you're going to have on your paper. So we'll just call this another example here. And we're looking for this common denominator. So I have an x here, I have an x minus 1 here, and I have x minus x. Well, let's just think about what the common denominator may be. Well, the biggest thing we have on this paper is this right here, right? Well, just think for just a minute. If I took x, let me do this over here. If I took x times x minus 1, what would that give me? Well, it would give me x times x, which is x squared. and x times negative 1, which is negative x. And look at there, if I multiply these two things together, it would give me that, okay? So that means that this x squared minus x is actually my common denominator, okay? So x squared minus x, okay, and x squared minus x, and x squared minus x. That may help us here just to keep in mind that this x squared minus x is actually the same thing as x times x minus 1, right? And we'll do that over here as well, because I think that'll make a little bit more sense as to why we're doing what we're doing. So again, that's the same thing as x times x minus 1. We could change that one as well. We really don't have to. What I wanted you to see here is what is going to eliminate. So actually what's going to eliminate is the x and the x. Okay, I cannot take both of those out. I can just take one out. And the same thing here. I'm going to have an x minus 1 that's going to eliminate, which means this x minus 1 will eliminate, but I'll still be left with an x. And then last but certainly not least, all of this is going to go away, and I'm going to be left with nothing but a 6. So let's take a look at what we're really left with. We're left with 2 times x minus 1, okay, because this is still here. I can't really just get rid of it, plus 6 times x, which is this portion right here, equals 6. Again, not too difficult of a problem here. We're just going to distribute out this 2 through everything, so I get 2x minus 2 plus 6x equals 6. So I'm left with 8x minus 2 equals 6. And if I add 2 to both sides, let's move my page down a little bit here. I'm going to be left with 8x equals 8, or x equals 1, right? And this should be our solution, x equals 1. What I want you to notice, though, is if I take that x equals 1 and I put it back into my original problem, notice what happens here. If I put 1 minus 1 right there, that equals 0. And remember, I can't have 0 on the bottom, okay? Notice over here as well, if I put 1 squared minus 1, 1 squared is 1, 1 minus 1 also equals 0, which is undefined, okay? So wait a minute, we just did the algebra, we just did the work, and it said x equals 1. Well, ladies and gentlemen, I want to introduce you to an extraneous solution. What that means is you actually found a solution here that you thought was correct, but if you plug it back into your original problem, it does not work. That means it is extraneous. Okay, so I'm going to give you another way to be able to solve this particular problem that will help you to know whether you have extraneous solutions or not. Okay, and you're going to say, why didn't you show us this a long time ago? Well, look at our original problem. We had 2 over x plus 6 over x minus 1 equals 6 over x squared minus x. Remember, if we had if we're trying to find the solutions to this, actually, if we could just figure out where x equals 0, then we know what the solutions may be, correct? And remember, when you're graphing, solutions are anywhere that it crosses the x-axis. So what we could do here is we could make this problem a little bit different. And what I'm going to do is just repeat the first part. But instead of this being on this side of the equal sign, I'm going to move it across the equal sign. Well, in order to do that, I have to make it a subtraction problem. So minus 6 over x squared minus x. So all I really did was I just moved this part across the equal sign so that it's equaling 0. And now guess what? I'm going to put this into the graphing calculator. Now I've already done this for us, but I wanted you to just see where I'm getting everything from. And so right here you see this 2 over x plus 6 over x minus 1 minus 6 over x squared minus x. And what I want you to notice is try to figure out where this thing is crossing the x-axis. Now, if you look, it looks like it's getting really, really, really close right here, but it never, ever touches the x-axis. And if you move over to the positive x-axis, look at this. This never, ever touches the x-axis. So, ladies and gentlemen, I have some news for you for this particular problem that we're working on. Even though you worked it out and you figured out that this actually says x minus 1, I'm going to tell you that this one, in fact, is no solution. because when you put the x equals 1 in, it does not make sense. It comes up as undefined. So this one is actually no solution, and you could figure that out by graphing. Graphs never lie. Okay, if that graph doesn't cross the x-axis, then it is not a viable solution. Okay, so you can graph these as long as you get them to equal 0 and actually see what that solution is as well. All right, that's all for today. And if you have any questions, make sure to reach out to us, and we'll be glad to help you with those.